Non-centrosymmetric materials was maybe discovered first in the paper by Ivchenko and Pikus in 70s, devoted to semiconducting tellur. Then some theoretical attention to these materials was almost absent. Only one paper was published by Ilyashberg and Levitov and Nazarov about electrodynamics of superconducting non-centrosymmetric materials, even in absence of theory of such materials itself. So the interest to these materials, metals, appeared already in 2004 with discovery first metal without center symmetry. It's cerium platinum free silicon by group of Bauer from Vienna. So and after that the theory was started to develop, and so my plan today just give you impression about the what is going on with such metals, how their electronic states constructed, and several effects like the Kasman-Alfven effect, magnetic susceptibility, and kinetic properties, magnetic electricity, and also there's some formulation superconductivity theory. This stuff for today is just due to the another part of my presentation devoted to altermagnets, which will be done Wednesday. But the theory of non-centrosymmetric metals somehow similar to the theory of altermagnets. And that's why I begin with this stuff. So this cerium platinum free silicon discovered by Bauer looks like as follows. And you see these atoms of platinum form in crystal lattice like an umbrella. And so the direction up and down different. So the reflection in the in respect of z-axis here, in respect c-axis, is not operation of symmetry. After there was discovered many materials of like this, but this another example like lithium to palladium free bore with structure with cubic structure. This is tetragonal crystal. This is a cubic. What we can say about the spectrum of electron state in this in such type of materials? So in absence of magnetic field, nevertheless, one can say there is electric field here because due to special direction along c-axis, the potential of atoms depend on z coordinate. So gradient of this potential is electric field, and due to relativistic transformation, one can obtain effective magnetic field. Looks like as follows. So it's just Lorentz transformation of electric field which exists inside of this crystal lattice. So and this interaction looks like as follows. In general, the role of this electric field plays some vector gamma, and this vector, so this is a vector product electric field on k direction of k vector of momentum, and play of this combination this role of this combination play vector gamma, and this vector gamma, due to the absence of inversion, is odd function of momentum. So of course the symmetry of this function should correspond to the symmetry of crystal in which we have such a situation. So in particular, in this material, cerium platinum 3, with symmetry C4V, I remind you what is C4V. C4V is a group of symmetry which consists of course, unit element, three rotations about the about c direction on the angle pi over 2, pi, and 3 pi over 2. So three rotations like this, and reflections in plane perpendicular to x direction, y direction, diagonal xy, and diagonal diagonal minus x y. Here is sorry, here it's a mistake. It's no bar here. So let's look first how this symmetry works, because I will use such a symmetry consideration during my lecture, and so one times look. For instance, let's consider reflection in plane perpendicular to x direction. This is a zy plane. So let's apply this operation to this combination ky x minus kx y. This is a spin vector in spin space. So it's obvious that reflection of ky not change with ky, because ky parallel to this plane, and x is a axial vector. What does it mean? It means it looks like a current around the x-axis. So this current, when we reflect it in the plane zy, in mirror will be the same. So there is no changes of such current at such reflection. So it means that this combination kyx is invariant in respect of sigma z. But the second term here is looks like as follows: kx perpendicular to this plane. So under reflection it changes sign. But ky y this axial vector change the sign also, because under reflection of a current around the y direction, this current change direction. So in general, one can say for any polar vector and axial vector transform in respect rotations in the same manner, but in respect of reflections, they change in the opposite manner. So application of this operation to this combination give the same combination. So this path in electron spectrum is symmetric in respect of this operation. One can check symmetry of this combination in respect of all this operation of symmetry. No, of course, this part called known in literature as a Rashba interaction, but this part necessary to add because it's three-dimensional material. Now, for this material, symmetry is cubic, and the gamma vector invariant in respect to all operation of cubic group is looks like as follows. It's just proportional to direction of k. So it means so mhm. So the spectrum in general looks like as follows. This is the even function of momentum. This is the odd function of momentum. And if you diagonalize this spectrum, we obtain two bands with energy epsilon plus gamma and epsilon minus gamma, whereas gamma is the modulus of this vector. So correspondingly, we have two Fermi surfaces determined by equations like this. And of course, two Fermi momentum, and each Fermi momentum depends on direction of k vector. And Fermi velocity determined as usual, like this. But in general, Fermi velocity for sheet with plus, not equal to Fermi velocity with on sheet with minus. Okay, Eigen functions for this space looks like as follows. So here it's a, you remember without this term, the eigenfunction looks like a 1 0 or a 0 1 here. But now there is a this splitting due to gamma, and so the eigenfunction looks like as follows. They are orthogonal, and also Kramer's dangerousness is lifted, because if we are playing the operation of inversion of time, the eigenfunction psi plus pass to the psi minus, but to psi plus and psi minus corresponds to different energies. This one. So there is no Kramer's dangerousness at all. Now two Fermi surfaces look like as follows. Direction of spin at each Fermi surface for cubic symmetry looks like as follows. Here outside direction, here inside direction. Of course, the splitting of Fermi surfaces it just exaggerated here. In fact, the distance between the Fermi surfaces is much smaller than Fermi momentum. For the Rashba interaction, it looks like as follows. The direction of spin is transversal to direction of momentum. So splitting once again much smaller than energy field. Now let's look on the first effect. It's the gas van Alphen effect. You know that at low temperature, magnetic moment of any metal starts to oscillate with magnetic field. And if we decompose this signal on harmonics, we obtain for each harmonic something like this. So the amplitude depending on magnetic field and temperature, of course, and frequency, and inversely proportional to magnetic field. So this frequency determined by extremal Fermi cross section of Fermi surface perpendicular to direction of magnetic field. But now, due to the band splitting, we obtain two Fermi surfaces, and we have, of course, each harmonic split on two pieces with lambda equal plus and equal to minus. So in concrete case of cerium platinum 3, for instance, Then gamma looks like as follows. The extremal cross section at kz equal to 0 looks like as follows. So lambda plus minus, so there is a splitting of extremal cross section, and so correspondingly we have two frequencies, f minus and f plus, and difference between them looks like as restored. This property was measured by Terashima, and indeed he found that this first harmonic was splitted on two signals with different amplitude, because this amplitude also depend on lambda. So, and due to this formula, one can establish with this band splitting is about 1000 Kelvin, which is much smaller than Fermi energy. Fermi energy is several electron volt. Here the splitting about 1000 Kelvin. Of course, measurements was done not on cerium platinum-free silicon, but in lanthan, because cerium material, it's a heavy fermionic material, and due to attenuation of signal due to heavy effective mass, it's difficult to measure this effect on cerium compounds. But anyway, this material have the same structure, noncentrosymmetric. Now, what about the susceptibility? As I said, the quantization axis always parallel to gamma vector. So it means that this equality looks like this. So, and one can look how this direction of quantization axis and distribution function changes under the magnetic field. Magnetic field is h smaller than mu Bohr h. So in this case, this epsilon looks like as follows. One need to add this h to this to gamma, and so if gamma we have the unit vector in this direction looks like as follows, and distribution function, Fermi distribution function looks like as follows. One can decompose in respect of small h both of this function epsilon and gamma, and after all we obtain with in the expression for momentum the following situation. So there are two contributions here. One contribution quite similar to usual Fermi liquid. It's just it's proportional to density of states on each Fermi surface, but with prefactor. And another contribution due to the space between two Fermi surfaces looks like as follows. Obviously, this part doesn't change in superconducting state, just because the distribution function in superconducting state changes only in vicinity of Fermi surface, but in between Fermi surfaces, distribution always the same. But this part change, of course. Now, what's important also here? It's important that due to this prefactor, if this distribution function depends inhomogeneous in space, in this case, in inhomogeneous case, we have because it's a tetragonal crystal, susceptibility in x direction coincide with susceptibility with y direction. But if there is inhomogeneity in space, in this case, this tetragonal symmetry disappears. So let's look on this. And this fact was measured experimentally. So it was done by Björn in Grenoble. What he measured? He measured the neutrons, inelastic neutron scattering. So this amplitude of scattering is proportional to correlator of momentum, like this, time-dependent correlator of magnetic momentum. So, and due to fluctuation dissipation theorem, this correlator can be expressed through the imaginary part of susceptibility. Then we apply Kramer's chronic relationship and calculating this value from experimental results, we obtain the real part of susceptibility. So, and he in fact measured the difference between susceptibility in B direction, so bidirection, and susceptibility in X direction, that is A direction. So, so it looks like as follows on experiment. So there is the anisotropy was found experimentally, but theoretical calculation shows that this anisotropy proportional to Pauli susceptibility, and the ratio of this anisotropy factor due to the spin orbit coupling divided by epsilon Fermi square. Anyway, it's a small value, but in fact it was successfully measured. In a cubic crystal, it looks like as follows. Here there is also imaginary part, but it's a theoretical result, of course, because experimentally measured in such a manner only a real part of susceptibility. Now, kinetic equation for such material looks like as follows. It was derived for any matrix distribution function by Victor Pavlovich Silin in 57. So it looks like usual Boltzmann equation, but now all the function energy and distribution function are matrices, and due to this reason we should, instead of usual combination like this, have a symmetrized product here and here also, and also some additional term. So this is a collision integral. So now the distribution function f, which is here, is an equilibrium distribution function plus some additional part due to external perturbation. So the path equilibrium part looks like as follows. So it's there is a diagonal part and off diagonal part also. Now it's difficult to work with such a equation in spin representation, and that's why one need to transform this kinetic equation in band representation. It's just formal procedure, so it's necessary to, by unitary matrix like this, transform any matrix like this to the band representation. Of course, we obtain part corresponding to equilibrium, this one, and plus this one, non-equilibrium part. There is some specific feature. When we transform derivative, it's not not so direct. It's not just a transformation from this to this, because this psi k dependent, and due to this reason, there is a commutator like this, appears commutator like this. So finally, if we, in presence of external electric field, we obtain the following equation. You see, this is the usual term, well known for one band metal. for each band, it looks like this, or with another band look like that. But there are also off-diagonal terms here. Here, this velocity is so-called Berry connection. And there is also off-diagonal term due to this contribution. So the collision integral has a awful form because one need to transform everything in the right hand side to the band representation, and due to this reason we deal with such combinations each time. But anyway, one can work with this equation, because if we say that band splitting much larger than one than the scattering rate, so for almost collisionless situation, it's always okay. And in this case, one can neglect the you see here there is a such a term which is proportional to difference between band energies, but in the right hand side, in the off diagonal terms, there are terms which are inversely proportional to tau, and that's why one can neglect, pardon, one can neglect by collisions for off-diagonal terms, you obtain the collisionless solution for this equation due to the comparison with term and this term. But for the diagonal terms, we use usual approximation, Tower approximation, and so with for tau plus and tau minus, we have two equations which in principle one can solve numerically, but not necessary for our following purposes. So now let's calculate magnetic moment in presence of electric field. So magnetic moment, it's just sigma vector Pauli matrix times with non-equilibrium distribution function. So again, one need to go from spin representation to band representation, and so in our words, let us transform each Pauli matrix to band representation and obtain complicated expression for sigma x, sigma y, and sigma z. So, and substituting this expression to this under this integral, we obtain a component of magnetic moment in presence of electric field. It expressed through this function G plus, G minus, G minus plus, G plus minus, and each of them, we remember, has the following form proportional to electric field. So in general, we see even if electric field directed along x direction, we obtain magnetic moment directed in any direction, because this is a very complicated combination. And this one, and this one. So we obtain magnetic moment proportional to electric field, magnetic-electric effect. On existence of magnet-electric effect in semiconductors was first pointed on by Ivchenko and Picus, and in metals by Edelstein. So usually it formulated as proportionality to not to electric field, but proportionality to component of current. For current, we should make the same procedure, transform from spin representation to band representation, and obtain the following formula. So, and again, the current proportional to electric field, and this part expressed through this combination, which is known as Berry curvature, but for this gamma is, you remember, odd function, and there are three odd functions here, and due to this differentiation, the property of odd property of this combination doesn't change, so this integral in current disappears in case of magnetoelectric effect. But I derive it just because it will be important for when we treat altermagnets. So we obtained two formula: electric current proportional to electric field, magnetic moment proportional to electric field. So we can express this as inverse matrix for to conductivity, resistivity, and obtain that magnetic moment proportional to current in non-centrosymmetric materials. This is a kinetic effect because both of these value A and rho, A proportional to time of scattering. Rho is inversely proportional to time of scattering. But in both cases, these are matrices, and so no constellation between tau here and tau here. Edelstein treated this approximation when tau plus equal to tau minus, and they obtain this effect like a thermodynamic effect. This is of course not correct because it's a kinetic effect, non-equilibrium. Now, several words about if we include electron-electron scattering. You remember that resistivity due to electron-electron scattering in absence or in presence unclub processes was derived by Landau and Pomeranchuk as proportional t squared. But in absence of unclub processes, momentum relaxation absent because momentum due to scattering electron on electron conserved, and due to this reason there is no such a temperature dependence, and all the resistivity determined by impurities. Of course, in two-band metal it's not the case, and for resistivities have a two contribution due to impurities and due to electron-electron scattering. It was derived by Dmitry Maslov and collaborator. The same law can be obtained for a non-centrosymmetric metal again when band splitting much smaller than energy Fermi, and scattering of rate on impurities much smaller than band splitting. So it's this calculation a little bit more complicated, by quite similar to this to usual two-band metal. Now let us ой, что такое? Let's look on superconducting properties. The usual BCS Hamiltonian looks like as follows, and in this case one can add the the singlet pairing and triplet pairing because there is no defined parity, and this part even function, this part odd function, but one can add both of them because there is no different parity. So again, like in normal case, one can transform this Hamiltonian to band representation and obtain the following form. This part we know, it's just narrow part, and superconducting part looks like as follows. It's a pairing inside of one band. Look, lambda the same here, and here also lambda the same. It's so, and it looks and this matrix element looks like as follows. T is a phase factor, looks like as follows. The transformation from here to here for an even part is exact, but for a triplet part is not exact because there are a lot of different terms due to interband pairing, but one can neglect by interband pairing here because band splitting is much smaller, much larger than critical temperature to transition to superconducting state. Corresponding Gorkov equations look like as follows. It's completely the same as in two-band superconductivity. The solution for each band, here you see, lambda is the same lambda. So, and here the pairing again, lambda, with opposite momenta, but with same lambda. So, the usual Gorkov theory, and it's instructive to look on this situation for pure BCS case. In this case, this matrix looks like as follows. It's a unit matrix, and this is sigma x, Pauli sigma x. So it looks like 1, 1, 1, 1. So from the left side, we have this equation from the left side for lambda plus here, lambda minus here. In the right, we have product of this matrix to such a column. Here the density of states in the band with plus, and here density of states with band with minus. We see by just multiply this matrix to this column, we obtain that the delta plus equal to delta minus. It's a trivial fact if of course any pairing like this is absent. Now it's interactive to look on this in spin representation. In spin representation, its Gorkov equations looks like a matrix equations because each function is now a matrix, and this P operator looks like as follows: lambda plus minus with unit vector of gamma again. Delta is combination of delta plus and delta minus, and if we substitute this P operator here, we apply the following formula. So this is just even part of order parameter. This is odd part or triplet part of order parameter here. To find the critical temperature, one need to return back to this equation. So you remember that this function looks like as follows. So now one need to decompose it over the function of irreducible representation of a group of symmetry of crystal, and so it's several representations. One need to take this representation which corresponds to maximal critical temperature. So in case of one-dimensional representation, order parameter looks like as follows: the path dependent of coordinate and eigenfunction of given representation here. So we obtain equations for two-band superconductivity. So each coefficient here is a product of matrix element of interaction, which is here, to density of states in corresponding band, and where critical temperature has a BCS form, but the constant which is in exponent looks like as follows. Now there are several interesting properties. First, London magnetostatics changed in non-centrosymmetric superconductor. You remember the London current looks like as follows. We see difference between the vector potential and gradient of phase. But in non-centrosymmetric case, one need to add such a term proportional to magnetic field, because symmetry not prohibits this term. Of course, they have different symmetry, but due to absence of parity, it's possible to write like this. This one can calculate from microscopic theory, of course, this coefficient here, which is proportional to the density of superconducting electrons, proportional to the amplitude of spin orbital coupling. So looks like this. So in absence of gamma, it's equal to 0. London equation now, it's a usual London equation looks like as follows. You remember? Delta is London penetration depth. But there is a rotor of this term also. Now one must solve this equation, but one need to apply a different boundary condition. What kind of boundary condition here? You see, this term, this one, new bed, it's so-called gyromagnetic current. Gyromagnetic current, it's just new curl A vector potential. On the other hand, any current can be written as a rotation of some magnetization. So now, if we compare this expression with this expression, we obtain that inside of non-centrosymmetric superconductor, there is momentum proportional to vector potential. So the boundary condition now, it's not coincidence of a field outside the field inside, field outside and field inside. But they differ each other by the gyromagnetic momentum, which is proportional, we know, to vector potential. So one must solve this equation with this boundary condition. It was done by Levitov, Nazarov, and Mineev many years ago, and obtain strange formula that usual dependence is this induction along x direction. Usually, just there is Meissner effect, and this induction saturates in tends to 0 inside of superconductor. Now there is a y component of B due to this boundary condition, And so, in fact, magnetic field rotate, not only saturate inside of superconductor, but rotate in plane in plane XY. In fact, it's a very, very tiny effect. It's interesting, but very tiny, because the parameter determining this rotation, it looks like as follows. Again, here, nu, you remember, proportional to gamma, delta, the London penetration depth, and if you estimate this value beta at zero temperature, then ns equal to density of electrons, we obtain 1,000th. So it's very small effect. Anyway, interesting. Now, what can we say about Ginsburg-Landau? I will say about one band, single band. No, physically it means, what does it mean? There is a splitting, but one band below Fermi energy, another band above Fermi energy, and in this case, one can discuss only one band. But anyway, look, Ginsburg-Landau free energy looks like as usual. There are gradient terms, so it's a gradient. But there is a term linear ingredient, proportional to magnetic field. So it's due to absence of space parity. And this quadratic magnetic field due to just the Zeeman effect. It's a Zeeman suppression of superconductivity. And this term just quite similar to that I show you in the normal state. Again, combination gamma I, gamma J, so looks like as follows. So now, what's interesting? Interesting that sometimes in some materials and some direction of magnetic field, this combination, which is specific for such substances, completely absent. For instance, in symmetry C for V, and magnetic field parallel to Z direction, with kzx and kzy equal to 0. So Ginsburg-Landau equation has the usual form. So and critical temperature has just a just orbital part, suppression critical temperature linear in magnetic field, and then Zeeman part, suppression of critical temperature by Zeeman field. But sometimes it's not the case. And for instance, for substance with group symmetry D4, gamma vector looks like as follows. Gamma kzz not equal to 0. In this case, the solution of this equation has the following form. So here, this factor is just degeneracy of levels in the plane perpendicular to magnetic field, is usual degeneracy. But this is not usual. It's the dependence of other parameter from z coordinate parallel to magnetic field. So the critical temperature starts to be a function of Qz, not degeneracy. So one need to the value of this Qz by minimization of this, or maximization, in fact, this critical temperature, and obtain finite value of Qz proportional to value of magnetic field and this coefficient. So you see the critical temperature now suppressed by magnetic field by orbital effect like this, suppressed by Zeeman effect like this, but stimulated by this spin orbital interaction like this. There is no cancellation of these two terms. One can show, in fact, that this term larger than this one, but so still Zeeman suppression exists, but it's a suppression smaller than these materials. And this one consequence, another consequence that superconducting state is inhomogeneous. Now, let me conclude. Let's summarize what we know today. Non-centrosymmetric metals, they are two-band metals, always, with two Fermi surfaces. Fermi surface splitting can be measured by the gas van Alphen effect, and it was measured in many materials. Spin is spin to momentum direction. There is some specific contribution to susceptibility determined by electron states between two Fermi surfaces. Inhomogeneous part of susceptibility is anisotropic. There is a non-equilibrium magnetic electric effect. Superconductivity also two-band superconductivity. With pairing determinant both singlet and triplet components. In Meister state, field rotates inside of superconductor. In some materials with particle symmetry, there is equilibrium magnetic electric effect leading to inhomogeneous superconducting state. So this in superconducting state, magnetic electricity is thermodynamic effects, unlike to normal state where it is non-equilibrium kinetic effect. So thank you.
Okay, let's thank speaker. And now questions. Okay. So, Sergey? Okay, then let me ask my question. Yeah, Vladimir, it seems to me that your last part concerning superconductors should be quite similar to the recent study of hybrid structures with Rashba interaction. I mean, bilayers of superconductor ferromagnet with a strong spin-orbit interaction at the interface. It looks like quite similar invariants in Ginzburg-Landau theory appear also in this case. Could you comment probably on that?
But this correspondence is trivial. It's just if there are such terms, they exist in Rashba case, they exist in any other case, and so it's you said just about a particular case of this situation.
Okay, so Sergey?
Vladimir Petrovich, thanks a lot, first of all. This is Sergey Streltsov. So my question is about microscopic physics, so related with non-centrosymmetric metals. So is this DMI which is responsible for all these effects, or anything else, like for magnetic electric effects? Дзержинский Maria, I mean.
Is there okay? The question is okay.
The question is about microscopic origin of, for instance, magnetoelectric effect you're discussing.
No.
Yeah.
Magnetic electric effect, you see. No, first of all, about microscopic theory. This equation about the calculation of this, for instance, this splitting. It was done, for instance, by Harima from Japan, for many materials, and he confirmed with value first. So
No, this is just exchange splitting, you mean? And that's
no. It's not completely not. It's not exchange splitting. It's a spin orbital splitting.
spin orbit. Okay.
It's a completely as look. This is a completely spin orbital split. No, it's no exchange at all here. So, and calculation by Harima-san was done with real material, for instance, with this material, taken into account with asymmetry of positions. And if there is asymmetry of positions, there is spin orbital coupling, and due to this reason, we obtain this term, and this also, and he calculated this. So not related to exchange. Now about magnetoelectric effect. In magnetoelectric effect, look. Well, let's take this term. This term is odd function of momentum. Gamma, all the component of gamma, odd functions of momentum. And this G plus also odd function of momentum due to V plus. And due to this reason, this integral is not equal to 0. If for instance, as in altermagnets, this gamma is even function of momentum, there is no magnetoelectric effect at all. So it's a just direct consequence of spin orbit coupling, which is odd function of momentum.
All right. Oh, yeah. Thanks a lot. So I lived in another world, probably like localized electrons with localized spins, of course. And this is a kind of metal effect. Yeah. So that's different. So splitting because of spin orbit coupling. But yeah, another way.
Okay, more questions? So my question is connected with the your talk about the proportional between the magnetic moment and the current, and you mentioned that it's not the thermodynamical stuff; it is pure kinetic, because there is no total cancellation of the relaxation time because of matrix. And what are your prediction for the experimentalist? If I put the some permanent current, what I'll see as for the magnetic moment, I'll see some response for the nanosecond and then the decay, or what is it?
Sorry, it's a good question. Unfortunately, I didn't take some corresponding transparency, but it was measured. So in presence of current, the appearance of magnetic moment was measured experimentally by several Japanese groups. And first of all, it was done for after the work of Ivchenko and Picus in semiconducting tellurium, but then in many other materials, it was just experimentally measured appearance of magnetic moment due to which is proportional to current, and also this statement that current, for instance, in x direction, but magnetic moment directed in any direction, it was confirmed experimentally.
But you mentioned that there's no thermodynamic now.
So it's not thermodynamic, of course, because it's a dissipative current. It's not superconducting current. It's a dissipative current.
Магнитный момент уже больше не затухает, и если я поддерживаю ток, он так и остается?
Конечно.
Все понятно. То есть в этом смысле он как бы нормальный, то есть, потому что там все понял, спасибо.